Okay, so I'm going to give an update on a Keck Institute workshop that we had back at the end of 2018 on tidal heating, lessons from Io and the Jovian system. The goals are to address the questions, or in general for these Keck studies: what is the current state of knowledge? What measurements are needed? How can these measurements be acquired in future decades? What technologies need to be developed and matured? What data analysis is needed? So here's a look at our happy group from the first meeting. Lots of people who know lots more than I do about most of the topics I'll discuss here. And then there was a follow-up meeting. We realized that we didn't have enough expertise on isotopes to understand long-term evolution. One thing they like doing at these Keck studies is make you do silly things to, break the ice. So tidally heated ocean worlds, what are they? Io may have a magma ocean, and we've heard a lot of talk about magma oceans here. There may be a magma ocean in our solar system today. We don't know. But mostly we're talking about water oceans. So Europa and Ganymede are both tidally heated, have water oceans. Callisto has water, but is not tidally heated today, certainly. And the Saturn system, Enceladus, is tidally heated and has a subsurface ocean. Titan is also tidally heated, not significant. It also has an ocean. It's not significantly tidally heated today. There may be other satellites, small icy satellites in the Saturnian system with oceans. In the Uranus system, some of them may as well, like Ariel, and the Neptune system, Triton is a good candidate for an ocean world. Pluto has been discussed, and of course, exoplanets and exomoons. Who cares? Tidal heating is a fundamental planetary process. It's important to the early Earth-Moon, outer planet satellites, exoplanets, and exomoons. It can maintain oceans over geologic time and sustain chemical disequilibria needed for life, especially if the ocean is in contact with a silicate core. Why an emphasis on the Jupiter system? The Laplace resonance of Io, Europa, Ganymede is unique in our solar system, although not elsewhere necessarily. And Io is so intensely heated that we can see the widespread volcanic activity and easily measure the heat flow. Why now? We have the Europa Clipper and JUICE missions on the way to the Jupiter system that will provide important new data. And exploring Io would fill the major gap in understanding the full system. So the key goal of this workshop is to determine the next steps. What do we know about tidal heating? So Laplace described the 4-2-1 resonance at Jupiter in 1771. That's illustrated in upper right. Every time Ganymede orbits once, Europa orbits twice, Io 4 times. And the significance of this took a little over 200 years to be realized, and Peale et al. Published their famous paper, Melting of Io by Tidal Dissipation. So this resonance creates significant force eccentricity in the orbits of the innermost satellites, Io and Europa. So they are periodically deformed by massive Jupiter, generating internal heating. Peale et al. Predicted a runaway melting of the interior of Io, thinning the lithosphere so that it could conduct away the heat. And they predicted that the Voyager spacecraft might observe widespread and recurrent volcanism. Famously, because only a few months later after this was published in Science, Voyager 1 went by, and sure enough, widespread volcanism. Voyager 1 also showed mountains up to 17 kilometers high. That's not so consistent with the thin lithosphere. The Galileo mission contributed measurements of magnetic induction signature for all 4 of the Galilean satellites, thought to be due to salty water in Callisto, Ganymede, and Europa, magma in Io. And there's possibly evidence for ultramafic lava on Io, very high temperature, which is most readily explained, at least with a magma ocean. The Cassini mission to Saturn, recently completed, showed that Enceladus have active jets emanating from warm fissures, evidence for subsurface oceans in Titan and Enceladus and maybe elsewhere. And also the astrometry, just measuring the orbit migrations of the Saturnian satellites, is an interesting result I'll say more about. And then, of course, we have the many telescopic discoveries of exoplanet systems. So we've already heard a lot about the Trappist-1 system, 7 Earth-sized planets in a close orbit with short orbital periods. This is a tidal heating wonderland, and Barr et al. Studied this, and from their model, planets B and C experience enough tidal heating to maintain magma oceans in rocky mantles. Those planets and planet C may have surface eruptions of silicate magma, which is good because you could detect it with telescopes and get some information on internal compositions. And then even on the more distant planets, D, E, and F, the tidal heat fluxes are 20 times higher than Earth's mean heat flow, and that may be sufficient to maintain water oceans at the surface and or subsurface. Okay, so what did we do at this workshop? One of the things we did was to identify 5 key questions. One is, what do volcanic eruptions tell us about the interior? And remote sensing can address this question, so that's good for studying exoplanets. Number 2 is, how is dissipation partitioned between solid and fluid layers? This really needs more lab work combined with modeling to interpret the observations. 3 is, does Io have a melt-rich layer that decouples the lithosphere, i.e. a magma ocean, or some other kind of magma distribution in the mantle? The tidal heating models vary drastically depending on this internal distribution of melt that's unknown in Io. So we can answer that question with magnetic induction, measuring the tidal love numbers, K2 and H2, and measuring the libration amplitude. Not sure we can do any of those measurements for exoplanets anytime soon. Number 4 is the Jupiter-Laplace resonance in equilibrium, and that we define that as the tidal heat generation equals the heat flow, and that's tidal heat generation in all of the bodies and heat flow from all of the bodies combined, but mostly it's Io. And one way to do this is to measure the total heat flow, including the polar regions, but this is difficult to do, and we don't know how it varies over time. But another way of doing this is to measure how the orbits are changing. From this, measuring in particular the orbital axis and how that is changing over time, eccentricities and related to that, as I'll say more about. Then the 5th question we came up with is, can stable isotopes inform long-term evolution? If you look at Io or Europa or Triton, you see a completely young surface. So there's very little information there about what happened in the geologic past. But isotopes can preserve that information. So we get to learn about lots of things outside our fields of expertise, which is a good thing about these Keck studies like this workshop. So one of this is about rheology. So material properties are strongly frequency dependent. These are a couple of plots here for shear modulus and dissipation, 1 over Q. Q is the quality factor for dissipation. And the x-axis is oscillation period. And so major differences with oscillation period, which is, we actually know a lot about very high frequency oscillations for seismic studies and low frequency for permanent deformation, but most of the tidal time scales is in between. It's anelastic, and that is not as well understood. So just as there are gaps in planetary missions and telescope capabilities, there's gaps in laboratory measurements, which this is just one example. The influence of melt and water and other volatiles also makes a huge difference. So here's a little picture of the orbital architecture of the Saturn system. There are 2 satellite resonances, Mimas Tethys and Enceladus Dione. And so I put the title here, what is the most important science result from Cassini that few people have heard about? Tidal migration 101. You have tides in the primary that dissipates energy with tidal torques that push the satellite outwards. The rate of recession depends on the tidal love number divided by Q of the primary. And this outward satellite motion may result in resonances between satellites. And there's also resonances between satellites and the primary properties. But resonances between satellites excite the eccentricities and cause heating. So the measurement that nobody knows about much is the outward migration rates of these satellites measured by Laney et al., mostly with Cassini data. And this was quite a surprise. It's very different than what was expected. They're migrating outward at a much faster rate than had been predicted. And the Q of the primary, you might think it's the same primary, Saturn, it should be the same Q value, but apparently it is different for each satellite, and that's because there's a different frequency given based on the satellite period. And they have a data point for Titan now as well that I don't have on here. So, here's an attempt to explain what the expectation was prior to this result and the alternate theory of Fuller et al. So the dashed lines here, this is distance in Saturn radii versus time in billions of years. And the dashed line shows the expectations if you have a constant Q of the primary, that's constant both per satellite and over geologic time. And the assumption that Mimas is 4.6 billion years old, so it can't be so fast that Mimas ends up in the center of Saturn prior to 4.6 billion years ago. And based on that assumption, you get the dashed lines there. And that's a Q value of 16,000. But what these astrometric measurements show, and I can go back, more like Q of 10,000. So very different, or 1,000 to 10,000. The solid lines show if you assume that this present day Q of the primary for each moon is constant over time, what does that mean for orbital distance over time? Well, it puts these satellites mostly in the center of Saturn in much less than the age of the solar system. So in only 600 million years in the case of Mimas, and somewhat longer periods for the other satellites. So one way to interpret this is to say the satellites formed in recent geologic time, and that has been suggested, but it's a different time for each satellite. So the idea of something dramatically surprising happening multiple times late in geologic time is hard for some people to accept. Fuller et al. Came up with an alternate model in which Q of the primary varies over time. And so this is the theory of resonance locking, and this is a theory that comes from astrophysics, from the evolution of stars and how that affects planets, exoplanets. But this Fuller et al. Applied this then to the Saturn system. And the basic idea is that the planet's internal structure gradually evolves over geologic time from cooling, compositional settling, such as helium rain. So as the internal structure of Saturn changes, the frequency of resonant peaks can evolve on planetary evolution timescales. And so the idea is that if it's evolving in the right direction, then a satellite can be locked to that resonance. So it sort of surfs that resonance outward in time, and then you get a constant T tidal for each satellite. And this model then implies that Enceladus could have been tidally heated, maintaining the ocean for much of geologic time, which is more favorable than the thought that Enceladus only formed a billion years ago, or that the tidal heating is just a short coincidental period in time that we're currently in. Right, so is the Laplace resonance in equilibrium? That means that the heat flow from all satellites matches the heat production from tidal heating. Long-term heat flow is hard to measure. Volcanism can vary on a timescale of decades or centuries and create a lot of noise in that measurement. But there are hypotheses that it's periodic. So the heat production can vary over time strongly or be in equilibrium, constant over time. Likewise, then orbital eccentricity is going to either vary or be constant over time. So we can't, measuring the long-term heat flow from the whole system is hard to do, but we can measure the rates of orbital migration of these. And T-tide is defined here. It's basically the semi-major axis of each moon divided by the rate of change of that semi-major axis. So the takeaway message then is just by making close flybys of satellites, the best way to measure how these orbits are migrating is from close flybys in radio science. You can, in theory, do it with optical imaging, but the center of mass may not be the same as the center of figure and so forth. So close flybys in radio science is the best way to do this. And can measure the positions of these satellites to 10 meters, and therefore measure these orbital migration rates very precisely. So this was done by Cassini. It was not done by Galileo Jupiter because there was a failed high gain antenna, and the technology on the ground and so forth was not there to do the precision ranging. So we will get this sort of precision ranging then for Ganymede from the JUICE mission. It's possible for the Europa Clipper mission, although it's not currently a requirement, and that's an issue to work. I think we'll get it. JUICE will also give some measurement for Europa. But all the errors can be taken up by IO. So the punchline that I want an IO mission, is close encounters of IO is what's needed to then understand the whole system. Okay, so the fifth question is, can stable isotopes inform us about the long-term history of IO and other worlds? And we thought about this and concluded that, well, you have to understand the mass loss processes to interpret those ratios. And so that's step one, is just to understand these mass loss processes, which are quite complex in IO system. So Io erupts into Jupiter's magnetosphere, where the material gets charged up. This creates a torus, plasma torus of energetic electrons. In any event, the first step on this is just to measure what are the mass spectra coming out of Io. New technologies with promise to address these issues. It's a long list. How am I doing? Okay. Special cameras to measure tidal H2, the physical movement of the surface. Landed seismology, remote seismology with a landed retroreflector. Landed penetrator heat flow probes that actually work. High dynamic range thermal imagers, mass spectrometers, been a lot of improvement there. Optical comm, constellations of small sats. We really are limited by power in the outer solar system, so things like INSAR would be great. Either we need low power INSAR, or we need greater power sources that work in the outer solar system. Satellite orbiters can do a whole lot. We're going to do this for Ganymede with JUICE, and we still need a small Europa orbiter, by the way. Clipper doesn't do it all. And mostly we need the same things we need for everything in the outer solar system: more power, radiation design, etc. And a key recommendation then is an IO mission, which is my ultimate motivation for all of this. And so a competed IO mission could at least partially address the 5 key questions: remote sensing to address volcanic eruption compositions, measurements of magnetic induction, tidal K2 libration, and the lava competitions also addresses if Io has a magma ocean. Radio tracking with precision ranging to measure tidal migration timescale. Neutral mass spectrometer to begin to address stable isotope question. The question 2 about how tidal dissipation is partitioned between solid and fluid layers requires new laboratory work. I'll stop there.